welcome back. Hope you had good breaks. So we're going to look at, continue on looking at aspects of hypothesis testing, confidence intervals, expanding our methods to different types of data, different data structures, different designs. And last Friday, we looked at comparing two proportions. And today we're really comparing two means, but kind of in a special way. It's really where we have paired data. So the data are kind of before-after experiment. And so we'll look at methods for that and the setup. Right? It's really a design issue. If the data are designed with before-after structure or a paired structure, then we can't treat the two samples, two measurements as very dependent. We have to take advantage, take into account that correlation, and it's called paired data. Right? So there's a homework posted that's due Friday. There's a couple of problems from each of these sections on fine confidence interval hypothesis testing. Last time we were kind of going backwards through this section, and we did 9.4, which is on two proportions. So there's a couple pages, a couple examples on that. And there's a couple problems on this paired data. And then on Wednesday, we'll talk about two independent samples, and there'll be a couple problems on that. The book includes some slight advanced formulas for some things. Or mostly we can use the basic ones are mostly what is kind of standard, was implemented and usually reported, but it has a few details in there. We don't necessarily talk about all the details. So the idea of this section is that we have some data, X and Y, and they're measured on a bunch of individuals, 1, 2, up to n. And both variables are measured on certain individuals. Yep. Like X is measured on the first person, Y is measured on the first person, X2, Y2, down to Xn, Yn. And we're interested in, the average of X's versus the average of the Y's. But these are matched or synced up together, so that the two measurements are on the same units, right? Or corresponding pairs that are matched up there. So if we want to look at the average use of X equals the average of X's in the population, and use of Y is the average of the Y's. If we're interested in the difference of those, say use of Y minus use of X, the average difference is what we're interested in. Could be interested in, is that 0? Is it a certain value? What's a confidence interval for that average difference? Right. We're, because these are pairs, we're going to take a differences. Let's call that P sub 1. If I'm interested in writing it as the Y variable minus the X variable, I'm going to take those differences in the same way, right? And then the second difference is going to be Y2 minus X2. The last difference is the nth difference would be Y sub n minus X sub n. Right, and we get those differences there. So to look at these differences, right, is we're going to summarize the differences by taking the average of those, 1 over n, the sum over all the differences. And we're going to calculate the standard deviation of the differences, the usual sample standard deviation of n observations. Right, so di minus d bar squared, we add all those up. I'll call it the squared here, so I'm going to put a square root in there and divide over 1 over n minus 1. And we get the sample variance, the sample standard deviation, the square root of all that. And if these are, we were thinking about these actually, I didn't mention this, as quantitative measurements of some type, like the exam score, the type 1, type 2, blood pressures, time 1, time 2, maybe weights, time 1, time 2, maybe length of time that a machine operates before it fails under 2 different circumstances. Right? We can summarize the differences just like we would individual measurements. And so if we want to do a confidence interval for the average difference, here we're going to be centered at the average value of those differences, the sample difference, plus or minus. Now, these are quantitative measurements, and we don't have too many of them. Right? We're going to use a t-distribution with n-1 degrees of freedom, some value from that. And then we need a standard error of the difference. Right? The standard error of the difference is the standard deviation of those differences divided by the square root of n. That's our standard error. We're going to use a t-distribution with n-1 degrees of freedom for that, and that's going to be our confidence interval for the average difference. Right. It looks exactly like the formula for just a single sample, but in this case there's 2 measurements, we're taking the difference, so it can look like 2 samples even though we're going to treat it just like one. We can also do a hypothesis test. You can have that the average difference is some amount. Yeah. Often you're interested in 0, right? There's no change would be 0 or null. But in principle, you could put any type of value here. Let's just put a delta. This is a d. Versus an alternative that the change is not equal to that value. Well, in evaluating these hypotheses, we're going to compute a t-statistic. And we're going to take our average value that we observed in the sample minus that hypothesized value. Maybe it's 0, maybe it's some other thing that we're interested in, and divide that by a standard error. Right? Same standard error as before. The S of d over the square root of n. And assuming that the data are roughly normal, or we have a large enough sample size, so such a limit there seems appropriate. Assuming that the null hypothesis is true, then this thing has a t-distribution. Right? And if it's large, very large, very small, we're going to reject the null hypothesis. So this thing, we compare this statistic. So under the null hypothesis, we compare the statistic to a t-distribution with n-1 degrees of freedom, and we will reject the null hypothesis if the absolute value of our t-statistic is greater than some t cutoff value. Say, we have a 0.05 level test, then we would use a particular cutoff value from a t-distribution and conclude that it's not significant. And that's kind of the main idea of these things, right? And it's we'll take a look at some examples and talk about a few issues of interpretation and design. Yeah.
So just to be clear, for the to find the distance, the average distance or difference. Sorry, not distance. Difference. There we go.
Yeah.
It's just the just to you sum all the values of the of that you have all the differences, and then you divide it by the amount of numbers you have.
Yes.
Okay.
Yep.
I just wanted to make sure you had that.
Now that d bar, that average there, right, is equivalent to, numerically equivalent to, taking the average values of the y's minus the average value of the x's. Why is that? Because if each di's is replaced by a yi minus xi, right? Then you can split that up into two parts. You get the average of the y's minus the average of x. So numerically, it's the same as that. But in terms of finding the standard error, or the standard deviation, right, it's important to take the differences. Because the standard, if you take the variance of this one and the variance of this one and add them together or try to do something, there's a covariance term. Because we're assuming these x and y's in this case, because of the matching or the pairing, are related to one another. The high values go together on x and y, or maybe it's high and low, but anyway, there's correlation. So that that needs to be taken into account. So when we take the, you could, if you just had y bar and x bar, that's going to be the same numerical value as this, but to get the standard, the sample variance or the sample standard deviation, it's best to work with the differences. So let's look at some examples, right? So these are examples that I've taken from another book. Let's look at the next page first, right? And we can do it smaller, a little bit crisper. Okay. So, in part, I like showing these examples. Okay, let's see. Let's get smaller here. Okay. Escape. Right. So, in this study, we're looking at the impact of putting red lights in different areas, right? And seeing what happens. You know, often states will find areas that have troubles, you know, in terms of accidents or other problems, and try to do something about it, right? So they had the average number of accidents during a year for these 13 intersections was here, and then then some cameras were installed. Right? I don't know if you've driven around the Washington D.C. area, but out in the suburbs, there's all these cameras. Some of them are fixed point cameras near the schools. And if you go 10 miles, 7 miles over, you get a ticket in the mail. Right? It takes a picture of your license plate, and so it just slows down traffic because everybody knows that that's there. And there's these other ones that move around neighborhoods. So you don't know where they're going to be.
That's horrible.
The ones that really get people are the ones that the turning cameras.
They really charge.
Yeah, so there's cameras on the intersections. It's not every place, but a few bigger ones, so that if it turns red and you don't stop behind the line,
Right.
it will take a picture of your license plate and send you a fine in the mail. So I've saved a lot of money since moving up here.
They do that in New Jersey too.
Yeah, right. Well, that much traffic, it's, how else are you gonna, slow it down? I don't
Even
know.
Concord, New Hampshire has them.
Yeah. So this was before and this is after. In this case, I've taken before minus after. So a decrease, so if it's a negative, let's see, I've taken after minus before, I guess. 1.36 minus 360, and got negative 2.24. So if it's a negative value, it's a decrease in the average accidents that are there, right? So for these numbers, right, so that's the structure there. So let's shift to this one, so traffic lights. The average value of the difference, so in all there were 13 lights. The average value was a negative 1.0069, a few more decimal places. The standard deviation of those differences is 1.209. The standard error we want to use in each of these calculations is the S of D over the square root of n. So the 1.209 divided by the square root of 13 ends up being 0.3354. Right? We're going to want a certain t-value, so 95% confidence interval for the average change. We're going to want a t-value based on 12 degrees of freedom. Minus 1 or 12. And T-table that we did here. So if we want 95%, we're going to look up the 0.025 upper tail. 95% leaves 5% overall. Half of that's on one side. All right, so we're going to look up this under 12. And so 2.179. A little bit bigger than 1.96 because we have a small sample. 2.179. 5. So with that, you can do a confidence interval. And so confidence interval, or so E bar plus or minus our T value, S of D over square root of N. So it was negative 1.0069 plus or minus 2.179, and then S of D over square root of N. All of that is 0.3354. So the interval goes negative 1.74, negative 0.28. So these are and the data as it's described in there, as the number of crashes caused by red light running per intersection per year. Right. So it's not a lot of crashes per year difference, but hopefully you don't have any. Right? And this is all negative, so how do we interpret that in this context? So we've taken after minus before. Right? So in interpreting these paired things, you always have to keep track of what you're subtracting from the other one. Right? So if after minus before, the 95% confidence interval is all negative. Yes.
It means that the average amount of crashes has reduced.
Yeah. So we're confident, right, that there has been a reduction in this, right? If we did a hypothesis test, right, we'd probably be interested in 0, right? If it's 0, there's no change. And then the alternative is not a change, or maybe you would do it one-sided. In this case, you could make it that it's a one-sided. That maybe these cameras, are distracting to people, and people, slam on their brakes to avoid the cameras and things like that. So it kind of distorts how they're paying attention to the cameras and not the other traffic. So let's just do it two-sided. We would do a T statistic. Now D bar was the negative 1.0069. We divide that by the standard error, so this 0.3354. And the T value we would get out of this, the T statistic, is about negative 3. What do we conclude about the hypothesis based on this?
Reject.
Why do we reject? Well, we'd have to look up this reference. This would be an extreme value plus that amount or negative that amount looking on two sides. Right? And we're farther than that. Right? So we're going to reject H0 because our T statistic -3 is less than our T 12.025, or maybe the negative of that one, 1.79. It's more standard errors away, so it's more extreme. And because the difference is on the negative side, we're going to conclude that the traffic accident decreased. So that's mechanics. Any questions about? Does this mean that the red traffic cameras caused the decrease? Are they responsible? Is it conclusive that the thing that made the difference was the traffic lights? Anything else have done it? Are there any limitations to this study? Yeah.
Well, there is a little bit of implementation of, if you're wanting to do this for a national scale, for instance, Virginia usually has pretty mild weather. So where, if you were to do this in Vermont, for instance, it might not cause the same effect because stopping suddenly can actually cause you to spin out and have worse problems.
Right, right. So if you were trying to generalize this, you always should generalize from the type of data that you have, the population covered, to similar ones. Otherwise, it's an extrapolation of some sort. Right. So if you imagine, you know, there's 1,000 intersections of this type in the Virginia area. Among intersections of this type, right, would it make a difference? If it's a rural road and not the same kind of volume, same type of characteristics, it's probably not going to be exactly comparable, right?
Maybe the power was out at the drive-through liquor store.
Right, or something, right? There could be other funny things going on, right? But this design, so this issue of causation still enters into it, right? In this type of studies, you know, before, after study, and you know, you take the ones that are really bad one time, put in an intervention, and see if it gets better, right? There could be some confounding, right? There could be something else going on. Maybe there's, you know, a lot of media coverage about these because they say, oh, they're putting in these you know, these are the places that they're putting in because of all these accidents, and they're really dangerous. So maybe there's a media campaign going on as well. Right? Maybe there's, you know, just noticing that there's a change there. People pay attention, right? So maybe if they had taken out lights, people would say, oh, things are different. We got to be careful now, right? That maybe it's just the fact that there's an intervention, not so much that it was the lights, right, that is there. Plus, you know, just over time, maybe the volume of traffic has reduced. You know, that could happen. You know, maybe they open a new freeway or a new way to get around these areas. Maybe they put some restrictions in, you know, outside of that area to reduce flow, and it's made a change. So there could be other things happening at the same time, right? There is an issue of confounding. Okay. Another change. Okay. Change could have occurred. Right, between time points. That is related to the outcome. And so a different way, we can think about, well, how would you design a study to try to get away from just having that? Right? Any ideas how you might change the study design? Yeah.
You could maybe ask the media to be a little more low-key about it, like you put signage up at the intersection, but you
Yeah.
don't broadcast it.
Yeah, so you might have, some time for it to kind of, you know, discount the first 3 months or something like that they're there first months because it's in the news and it's all. Wait till it's kind of returned to a, you know, normal flow for that area. So there could be something to try to combat parts of that. Yeah.
You could see, you could break up the roads that you're looking at into a control group and a non-control group if you're
Mhm.
trying to just make sure, like, just any change would have caused something. Maybe you put a stop sign at half of them and you put the cameras at another half just to see if there's some change
Yeah.
that could cause.
Yeah, so this idea of a control group, right? So in this just before after, all these intersections are getting the stop lights, right? There's no control to nothing going on. And this is only one type of intervention, right? So so a different type of study, so you have a bunch of intersections. Maybe you randomize those to two groups, right? These get, you measure them before, as they are, you get their number of crashes before. Some of them get new red light cameras, right? And then others get, you know, nothing, no change. Right? And then you measure, you know, after a period of time, maybe you allow a little transition to kind of wash out the effect of the recent construction. Maybe you do it, make sure it's at the same time of year, same type of, you know, type situations. And then you compare change for these red light camera versions, and that's a decrease like we've seen, versus what happens here. Now, this one shows not as much decrease, or maybe a larger, or an increase. Then you have a comparison group going on. Maybe if these are in the same area, then the same kind of temporal changes in terms of changes in volume, changes in general behavior would be affecting both. And it would be more convincing that there's a control group. Yeah.
And would this before and after study still be considered an experiment because you are changing a variable, or would it be considered an observational study because you're still kind of seeing what happens?
So that just as it is in this case with just these 13, I think it was just observational, right? Because there's not a really defined control group. Each as contrast to this, where you have the red light camera versus change, right? You could have a third one that's, maybe you narrow the lines, you make them go. It's called calming, right? That you kind of make it look like it's narrower, and the people's response is to drive slower to compensate for that, right? So you could have a third group in there, and once it has these comparisons where you have the treatments, then it's really, really comparative, right? And that would be more of an experiment. The other one is more observational, right? So how, yeah.
It'd be interesting to see what would happen if we just put the sign saying there's a camera without actually putting the camera in, to see if it would still have the same effect.
That does, that's effectively what happens in some of the neighborhoods around DC, probably also Hartford and so on, that there's a sign that says monitored by cameras, and then there's these trucks that bring these things around and put them down beside the road, and then they're there for a while, and they take them away. So you kind of learn that certain neighborhoods get these occasionally, right? And if you speed through those all the time, then you're eventually going to get caught by one of those because you can't always see them and slow down. But anyway, to deal with that, you could do this. So you could also kind of do this thing as there could be a further level of pairing, right? In the sense that there's kind of before, after, it's going to be the basic measurement for each of our cameras, right? Let's say you had 26 intersections, and you could rank them, most dangerous to least dangerous. You could take, say, the first two that were the highest intersection, right, and then flip a coin, and one of those gets a red light camera, and the other one doesn't. Right, so you could create another level of pairing, so it's kind of a paired study, where this one, these two are the most dangerous. The ones that have the most accidents before, and then N, which is going to be 13 again, is going to be the least dangerous. In terms of their before measurements. And then you could do the change for the red light cameras, and you could do the D, maybe it's capital, so I'll do these, D for no change. And then these are essentially pairs, right? You have their reduction in the red light cameras, and you have the reduction in the ones that are not there. And they're paired by how dangerous they are. And you get to take differences there. Right? So one of the advantages of these differences is a reduction in variance, but we'll talk about that in a bit. So this experiment could also end up being a paired study. But any questions? Let's look at another example. We'll do some of these in R. So on the first page, with 9.39 from this other textbook. I like these examples because it sets it up as a paired study. It lists before and after measurements, and you have to see the differences there. Right, so this was a study, there's 9.39. What's the impact for elderly individuals of having some experience like going to a museum and handling these different objects, and how does that affect their mental health, their mood, their feelings about their health, self-assessment. Right? So there's a before measurement, and then they go and get this experience, and they ask them afterward, is there a significant difference there? Right? So let's look at how this would be computed in R. Right? So the basic data, right, is entered in a spreadsheet. Before and after, and the two measurements that for each person are paired there. So that's what the data looks like as it's entered into a spreadsheet. We go into R and read that in. It will be a table here in R with before and after on it. The data has columns before and after. You know, these are the first 5 observations, and the last 5 observations are these ones. But to do a paired study, one way to do the computations, right, is just take the differences, take the after minus before, so that if difference is positive, then it's an increase because after is bigger. Right? There's 32 observations that are there. The average difference is 7.625 on this 100-point scale of people's attitudes about their health, their ratings. Right? The standard deviations of those things are there. Let's look at a histogram of the differences. This little histogram of the 32 differences. You know, not too abnormal, too non-normal, right? Not exactly, you know, a little bit of skewness of those differences, but not so severely. No huge outliers, no extreme skewness in there. The average of those things, you put a vertical line at the mean, and I call just V bar the red. So there's the average of these things, right? And we want to essentially see, is there any, you know, so after is larger, so there's an increase in this measure, which is good. Is this significantly different from 0? Right? Is that average? Is this really convincing to us that there's an increase in this, right? So if we need to do you know, there's a standard deviation of those measurements. They're kind of here, you know, plus or minus a couple, you know, 2 standard deviations, you know, plus 5, plus another 5, plus another 5, plus or minus 3 standard deviations really seems to cover the range, right? So standard error is 0.392, degrees of freedom is in -1. The t-value that's important is this 2.035. Either we're going to calculate a t-statistic and compare it to that, or we're going to use that value as a multiplier in the confidence interval. The t-statistic, we take the d-bar, which was 7, divided by that standard error. The standard error, what's the standard error? Was just a little bit less than 1. So the t-statistic, which I call t-stat there, right? T dot stat, if I print it out, is 8.18. That's enormous, right? Way off the scale. The PT does a probability that you're less than a value, so the chance that a t distribution, you know, 8.18 is less. Let's see, there were degrees of freedom was 31. Is basically 1, right? It's almost 100% area below that, so 0% above. There's almost nothing down there at the tail. This is the value if you get it to actually print out that as a number. And so it's extremely small. Right? So we're going to definitely reject the null hypothesis that there's no difference. There seems to be a positive difference, right? So again, in this case, each person's their own control. Does their, based on this, is it clear that handling these museum objects and going to a museum is what caused the difference and caused people to feel better? They've done something to make them, you know, something's happened, right? Is this, yeah.
One of the things, especially with this one, that's kind of would be kind of deceiving is the fact that they're also, I'm not sure if they're necessarily, it doesn't say on here, but it seems like they might be going to get to the place to get the objects to feel as well. Like if you're just going out to a museum might be enough just to increase your health for a little bit.
Yeah.
So if you've been in a hospital room for the last 3 months, going out, just even outside can be helpful.
Yeah, so there's all these confounding things that happen. You know, if they're on treatment for something, they just might be getting better anyway. And all sorts of studies get done like this. Psychology, you know, behavioral studies, and so on, medicine, that almost any type of intervention might have a positive effect sometime or be measured over time, right? They could have brought in animals and had them interact with animals. They could have brought in school children to sing or something. And, you know, that something that would be just a difference. You know, if they've been in the hospital for a long time, almost any change could have that benefit. So again, if they set it up as a control group, right, then they possibly could have had, you know, and some people just didn't get anything, or they got something else where they just got a different change. You know, looking at multiple different studies, different interventions, you can kind of see that, and then also a control group there. They doesn't necessarily get anything different, or maybe they get a minimal, you know, maybe they get a pamphlet or something new to read, right? The really low cost version of this might be the comparison. Might they get a new information shared, and so then they get some intervention, but it's not the big cost of actually putting them in a van, taking them someplace, or making these special exhibits. So yes, it's significant that there is definitely seems to be an increase, but what was exactly the causal medicine? Was it specifically these museum items, or was it just doing some intervention we can't really help with this? There's something else that happened. So let's look at this one in terms of the variances. And so why is it important to really use the differences? The standard deviation over the square root of n as standard error. So on Wednesday, we'll look at 2 independent samples. So if we have x1 up to xn and y1 up to ym, I mean, if they're 2 independent samples, you don't necessarily have to have the same number of subjects, right? You just pair the matching as we do. And if you took x bar here and y bar here, you could take the difference of these 2 things and call it an average difference. The variance of this one would be estimated as the variance of the x's over n, and this one, the variance of this thing would be the variance of the y's over its sample size. Okay? And if they're independent, then the variance of y bar minus x bar would be estimated as the sum of the 2 variances. You know, everything gets squared in variances, and so we would estimate that, the little hat over there for the estimate, would be this s of x squared over n plus s of y squared over m. We treated them as 2 independent samples, but if they're correlated, right, then there's a covariance term in there. So how big is that covariance term? How important is it in this study? So we could take one group of people and measure them before, and take another group of people and measure them after they went to the museum. You know, the people that stayed at home, and people that went, and look at that difference, right? We could have 2 independent samples. What do we get out of actually measuring the people before, making the effort to measure them before and after, keep track of those records? Well, let's look at what it is in this case, right? So, big to the top. So we have those differences. Here are all our 32 differences. Here they are assorted, right? The standard deviation, you know, let's do the variance of these differences, is 27, right? But we would do variance over the 32, right? That's like the variance of the average difference, right? That's the variance of d bar. The variance of, what was it called, museum after, right, divided by 32 is that. and the variance of before is that. And if you add those two things together, use the after divided by 32, you get 6.6, right? So the variance of the differences divided by its 32 is 0.868. But the variance of, if it had been two independent samples with the same measurements, would have been more like 6. Right? So that's a huge decrease from 0.8 as a variance down to this. If we take the square root of those things, we get the actual standard errors. So by 0.93 versus the standard error we used, the square root of that, had they been independent samples with the same measurement, 2.45. So about 2.5 times as much variance versus taking this. Why do we get this big reduction in variance in this case? Well, let's look at a plot. I think this will plot the two variables. All right, these are the before measurements and the after measurements. Right, they're noticeably pretty highly correlated. Right, the people that are feeling better before are feeling better after, and the ones that aren't feeling so well before are still not feeling so well, but it's everybody's got an average increase. Right? There's a high correlation. The correlation of these measurements is actually 0.86, or the covariance of that is 83. That's a little harder. The variance before was 101. The variance after was 92, and the covariance is almost the same magnitude as those. Right? So the variance of the actual difference when they are paired, variance of y bar minus x bar is the variance of the y bar plus the variance of the x bar. Because the negative is minus 2 times the covariance of these two things. And because of the high correlation, this covariance is almost the same magnitude as one of those variances. So we get this big reduction because there's this positive covariance between these. So pairing makes this study highly significant. Whereas if they'd been two independent samples with similar measurements, it might not have been, right? Because the variance of the difference would have been so much inflated and you wouldn't have got this reduction from the covariance between the x and y's being similar. So in this case, the pairing is critical to making this study work out and have a significant result. Otherwise, you get this big. So pairing can give you real big advantages. If you think things are going to be highly correlated and you can do it as paired, then the change can have a very small variance, even if the individual things are highly variable. There's another effect that goes on that we'll revisit a little bit. When we do correlation and regression after the next exam, there's something called regression to the mean, where if you have two variables, x and y, and they're positively correlated, is that if you have an x value that's some standard deviations above the mean, that the y values tend to be above the mean, but not quite as much. The factors that make things extra high or extra low away from the mean, people tend to revert a little bit towards this center. And so when you have a plot of points, kind of a scatter plot of x versus y, that the regression line that would predict y versus x kind of goes through the center, but it's tilted down just a little bit. Right? So that large x values, if it in this positive association, are associated with large y's, but fewer standard deviations. Above the mean. In the Y variables, there's often a decrease in this. So if you were looking at the traffic lights that were the worst case scenario and then looking at them after a period of time, there's a bit of natural decrease that happens. Right? If you go out and take the ones that are absolutely the highest out of all of them that are there, well, they're likely to be high again because there's a positive correlation, but there's a little bit of slippage down. And it's just a statistical fact of how these things are going. And we'll quantify it more with the, when we look at regression. So sometimes you could have a decrease in the traffic lights, or for these individuals, if you had the people that had the highest, the worst health, they would tend to go up a little bit towards the middle, just by the fact that you're measuring them over time and there's this natural progression that happens. So again, it's hard to do causation unless you have a control group that's in there. But any questions about that little diversion? A little bit. We'll come back to that when we talk about regression and some formulas a little bit, right? So how about the last example for today, right? Where is it?
What about dementia?
Dementia, leisure activities and dementia. I just take a little. I'll give you some summary numbers. Why don't you take a couple minutes to write out formulas, expressions, have the calculator, you can calculate parts of it. Let's see if I can get the t-table up beside it. What I want to do. So, I need to do it again. Third column here, the .025 column. Either do a hypothesis test or a confidence interval, or just write out one of them. anybody want to report on what they did? What type of results did you get? Anybody do a confidence interval? Yeah.
So according to my calculations for the confidence interval, I got negative 3.864 to negative 0.042.
0.042, just below, right? So how did you calculate that?
So I first took the distance, to the average distance of D line
D1.
over thingy.
Oh, yeah, yeah.
To that, yeah.
Yeah, yeah.
Sorry. Plus or minus 1.960, which is the t-value that we're using.
Okay. 1.60.
Yep.
Um,
Or would it be?
You know, I might use 1 point, let's say we had 107.
Oh, so it might be a little bit between then.
Right, so
there.
it could be kind of like between these, so 1 point,
All right, my numbers are gonna be off because
just a little bit, but it'd be pretty close in any case. But I'll probably use something like 1.99 or round down to 2, because 1 point with the 107 pairs, right?
Mhm.
All right, so then we use degrees of freedom, 106. So somewhere in between these two.
I apparently did not see the 120, which is like,
Oh.
oh, okay, it only went to 60, and then like
Oh,
right,
so
so
yeah,
it
jump to the
like,
next one, yeah. And the conservative things to do is go down to the larger value. It makes the intervals a little bit wider.
Yep.
It's a little more conservative than we have to do. When we do it on the computer, though, we get the exact value. But what else did you do after that?
and then did plus or minus, well, sorry, yeah, that times the standard deviation over the square root of 107, which is the
Yeah,
n.
right. Yep.
And the calculation's right, it's just the wrong number.
Yeah, so it's just a little bit different than that. Did anybody get a different number?
I used 1.98 and got 3.88, negative 3.88, negative 0.02.
So this is 3.88 and negative 0.002.
That's using 1.98.
1.98, right. If you use 1.99, it would be just a little bit wider. If you use 1.99, does it actually go over 0? Not quite. This is really close, right, to that. So how would you interpret that interval?
That it is whatever we're looking at decreasing of onset of dementia, right?
Right.
So it would, even though within that confidence interval, I would say that it did decrease to a certain amount. I wouldn't say it's necessarily significant yet, because I still have to connect. You would still have to like.
Yeah, so is it practically significant, right? So it's a little complex in this, right? Because they're measuring activity levels, self-reported activity levels from 20 years ago of these individuals. And some people had dementia, some pairs in the twins had dementia, some did not. Right. Oh yeah, you can just set those there. Thanks very much.
You're welcome. Thank you.
Yeah.
Have a good day.
And they, so the ones that had dementia had less activity all that time ago. And the average difference in activity levels was about 2 hours per week or something like that. Leisure activity. Right? Oh, on an 80-point scale. It's a little bit hard to translate that into hours exactly. Right? But they seem to have a little bit less leisure activity. So this type of study is called a case control study. Right? So the cases in this case are the individuals with dementia, right? And the controls are individuals without dementia that are like the controls. Why is matching used in this case? Or how is matching used? What do you think are some benefits of matching in this case? Twins, right? So they can have, if dementia is somehow genetically associated or associated with family circumstances, diet, exposure, and they grew up together, and twins, a lot of things are the same. But just whatever reason, one twin had dementia at a certain age and the other one didn't, and then they're able to look back at these times. Right? So thinking about this seems like an enormous undertaking, right? They collect the data 20 years before or sometime before, save it all that time, and then follow up with these individuals, right? But that's, how else are you going to do something like that? If you're going to take individuals and then collect a bunch of data, you know, so in that case, it's kind of perspective, looking forward, but it's following everybody every year, trying to maintain their, find out about their health status, things that are happening to them. Right, it's a huge undertaking. So it doesn't include zero, but is it practically, you know, there's a lot of questions how they interpret this type of self-report, behavioral data that makes it a little bit difficult, but it kind of builds evidence that maybe, you know, you could suggest that having the activity would seem to be associated with decreased dementia. Did anybody do a hypothesis test for this? So, did anybody compute a T statistic?
I just did.
Okay.
So we would take the distance, the average distance, which is negative 1.953, and then divide it by your standard error, which is the same number as the that you just calculated. So I got 0.975 for the 10.0821 my divided by the
So it was
square.
1.975 or 1.975?
It was, no, for the number itself.
Oh, okay.
No, for like what you were dividing it under. You
Uh-huh.
I got
Oh, 9.975.
I got 0.975 for that.
Yes.
And then for my T statistic, I got 2.003.
2.00. Right. Or even, you know, whether it's positive or negative, it's negative 2.00.
Negative, yeah, sorry, it
But
was
with a
negative.
two-sided hypothesis, so if there's no difference versus there is some difference, one way or the other, this one, not quite past 1.96, 1.98, 1.99. Right. So it's just a little bit past that. So reject the null hypothesis and include that there is some difference, right?
Even when it's so minimal, you would still reject?
Yeah, so it is a rejection, so it's statistically significant. It is just beyond that. It's a 5% cutoff level. I mean, it's the p-value, if you reported that, it's something like 0.049 or something just about that. When we go into R, there is a t-test command. So the names on the dementia data right, are here, the first three rows of that data. There's the control and the dementia and these, right? If there's a t.test command, right? And so you can put the controls into there and demented, right, in there. And it treated it as two different samples, so you have to tell it that it's paired. Right? You tell it's paired equals true, it reminds you that you're doing a paired t-test there. Right? A t-statistic 2.004 with rounding, degrees of freedom. It gives you a p-value here, 0.04762, just below 5%. Right?
Well, if it was above 5%, you wouldn't.
Right. Yeah, you would not reject. And so I think, you know, the confidence interval, it happens to have taken the control, which did more exercise, more outside time, versus minus that's okay with positive values. And so, you know, more descriptive is the average difference in that point scale, the confidence interval, the actual p-value that it's right at the level. Just saying it's below or above doesn't give you quite as much information. So it's kind of on the borderline of this, and so maybe that's something that's relevant and help, yeah.
All right, so one of, just a question of how the information was taken. It's saying that it was from the Twin Registry database. So does that mean 20 years ago they measured how much they were exercising, how much they were doing, or did they ask the twins themselves how active they were?
Yeah, so the active overall leisure activity measured on an 80-point scale. So they must have, probably they asked them, maybe a survey item that asks, you know, how many hours do you spend doing this or this or this? You know, how do you divide up your day or your week? Maybe they, you know, you could give them a card, you know, a booklet to fill in. What did you do during the day? You know, and you write in the hours, kind of a more like an ongoing activity record. Or they could ask them in the last week, how much time did you spend doing these different things? So some type of measurement like that, right? You could make it more scientific. You could give them, you know, Fitbits now, right? And have them walk around with Fitbits for a year or a month or something like that, and compensate them somehow for participating in that. You know, that could record a whole lot of biomorphic data about them. And if you followed them up 20 years, 40 years down the road, you could see, is that associated with how things turned out for them?
It just feels like it has so many confounding values or confounding variables that could interfere with this conclusion.
Yeah, so if this is one study along with many that shows some benefit of exercise of different times, you know, then you kind of build up what is the impact of exercise and activity over a lifetime. And it's not going to be solved in one study, but, you know, it's kind of suggestive that there's some positive benefit, and, you know, maybe you would see that in other things, not only in dementia, but in cancer or in other survival. Anyway.
Great.
Yeah.
And you want to meet at your office at 2:40?
Yes.
Perfect.
I'll come on. Yeah. Yeah.
How was your break?
This should be,
Yeah, it was a bit rough.
what was there was different.
At first, that was night I did, so like, good, but it was like,
Yeah, it might
now
not
it's
be.
much more
Might be a square.
drawn out process. Otherwise, it's pretty good. I had a conference. My sister for a week, and I figured out what I've gone.
What did you get taught?
I might have gotten caught. Yeah.
I do get
taught.
That's right.
Yeah, but it was my fiance's car, so I feel bad. Yeah, they'll get the ticket.
Good idea. Take care. Thank you.
Should we go home or what do you do?
I'm actually taking to do a summer class at UVM. It's just it's an online French class.
Sounds absolutely horrible.
Just checking a box. You know, I know enough French to order a beer, that's pretty much it.
Take
care.
Languages are 5?
Yeah.